Well, hey everybody. Today we are going to get to talk about waves and wave properties. This is Unit 8, Day 3 on waves. So glad that you could join us today. When we talk about waves and wave properties, so far in this unit, we've been talking mostly about pendulums and springs. And this is about the point in the unit where students start to ask me, okay, Miss Wilson, we've been talking so much about pendulums and springs. When do we actually start to talk about waves? Well, that would be right now. But before we do, let's talk again about pendulums and springs. Here's the idea. I'll show you the setup. Imagine that I had a little spring right here, and I had a little mass on the end. And now imagine I tied a little marker onto the end of my little spring here. Here's my little marker. Let's make it a, wait for it, purple marker. Yes. Okay, so here's my purple marker. And here's what I'm going to do is, we'll color it purple. Yes. Okay, here's my purple marker. Now let's say I took my purple marker and I took a sheet of paper and I held up that little sheet of paper. Oh no. I held up that little sheet of paper right here in front of the spring. Now, can you imagine what would happen if I took this spring right here? I pulled down on the spring. Pull down, pull down, pull down, pull down, pull down. And then I let it go. Well, if I let it go, as the spring bounces up and down, the purple marker would make a line up and down on this piece of paper. Now here's the idea, and this is going to take some 3D orientation of your brain, so see if you can do it. Imagine if I had this spring bouncing up and down with the purple marker attached to it, and I grabbed this piece of paper by the side, and as this spring was bouncing up and down, I pulled the piece of paper to the side so that the spring, as it's bouncing up and down, that marker is making lines on that piece of paper. Well, when I look at that piece of paper, after that little marker has been making little lines, what I'll see on that piece of paper is something that looks like this. On that piece of paper, when I take a look, I'll see, no, thank you. I'll see this. A nice sinusoid. A nice wave-like shape. Here's another example. Let's say that I had a little pendulum like this. And I took that little pendulum, and to the side of that little pendulum, I attached a little purple marker. And let's say that I took that little pendulum with its little purple marker, and I pulled it back. And then underneath that little purple marker, attached to the little pendulum, I put a little piece of paper below it. If I did that and I let the pendulum swing back and forth, like into the screen and out of the screen and into the screen and out of the screen, if I let it swing back and forth like that, then the purple marker would make a line on the piece of paper right where the pendulum is swinging. But if, as this pendulum was going, I pulled the piece of paper to the side underneath the pendulum as it's swinging, then when I let the pendulum go, it'll swing back and forth as the paper is moving. And when I pick up the piece of paper at the end and I take a look at it, it'll look like this. It'll have a little wave shape on it. Here's the idea, and here's why we've been talking so much about pendulums and springs, is because pendulums and springs oscillate. And you know what else oscillates? A wave. In fact, it turns out that all waves are made of little particles that are just bouncing up and down like pendulums or springs. That's all they're doing. They're going back and forth and back and forth and back and forth. And so I like to say that pendulums and springs are the basis of all waves, and that all waves have their roots in little particles that act like pendulums and springs. That's a little intro to waves and why we've been talking about pendulums and springs for so long. Now, before we talk about waves, we should probably get a nice definition of a wave. A wave, I like to say, is a disturbance in matter that transfers energy. Wave is a disturbance in matter that transfers energy. Here's what we mean by disturbance in matter. Have you ever seen a ripple on a pond before? If you've seen a ripple on a pond, then you've seen a wave. And the way that a ripple on a pond happens, you know this, is you take a rock or a bouncy ball or a hand and you hit the water. When you hit the water, that disturbs the matter. That disturbs the water. And so you get a big change in the way that the water looks. The water moves. And then, as a result, this ripple spreads outward. It all starts with a disturbance in matter. Let's talk about the second part, the transfer energy part. Well, here's how it transfers energy. Before, all of that water was sitting there perfectly still. But now that you've thrown a rock into it, some of it has started to move. Some of those particles used to have no kinetic energy, but now that they're moving, they have some kinetic energy. And then as the ripple spreads, the water particles that are sitting right next door, they start to move. And so now those particles that used to just be sitting still, now they have kinetic energy. And as the ripple spreads even further outward, these particles that are sitting out here, that used to be sitting perfectly still, now they start to move. And so now they have kinetic energy. And so it's this spread of kinetic energy outwards. So you can see that a wave begins with a disturbance in matter, and it's a transfer or a movement of energy outwards. There's one other vocab word that you need to know before we talk about some other properties of waves and some different types of waves. And that vocab word is medium. The medium is the matter a wave travels through. The medium is the matter that a wave travels through. If your wave is a ripple on a pond, then the pond is the medium. If your wave is a sound wave in air, then the air is the medium. The medium is the matter that the wave travels through. Now, here's one thing that's really important to know about waves, and it's one of the things that I say for today is one of the biggest ideas. One of the biggest ideas about waves is that when a wave moves, the medium doesn't move. It oscillates in place. It's the energy that travels. And I would write this down as a sentence if I were you in your notes, something like this. In a wave, the energy travels, but the medium, or another way to think about it is the matter. Another way to think about it is like the particles that make up the wave. I'm going to say, whoops, little eraser here. Oscillate in place. A lengthy sentence, but an important one. In a wave, the energy travels, but the medium, the matter or the particles that make up the wave, those just oscillate in one place. They don't move with the wave. I'll show you a few examples. We'll look at some simulations of this kind of thing, but here's the idea, is that if a wave is moving, the particles of matter that make up that wave, those aren't moving with the wave. The example that I use in class that students find helpful is I talk about the wave at a baseball game. If you've ever been to the baseball game, then you know at the stadium what happens when people do the wave. And you definitely know what doesn't happen. When you're about to do the wave at a baseball game, what does not happen is that all of the fans in the stand do not take out their running shoes and lace up their laces and then get ready in the running position to run around the whole stadium with the wave. That's not what happens, because the fans know that's not how the wave works. What they do instead is they sit in their seats. And then they wait for the wave to come to them. They can see it moving around the stands. When the wave gets to them, they all in their seats stand up like that. And then they sit back down in their seats. And that's the wave. Notice, the wave travels around the stadium. But the people, the little particles that are in the wave, they don't travel around the stadium. The wave travels, but the people just oscillate up and down in their chairs. That's how all waves work. In all waves, the little particles of matter that make up the wave, like if it's a wave in the water, the little water particles, they don't go along with the wave. What they do instead is they bounce up and down as the wave passes them by, just like stands and the fans standing up and sitting down again when the wave passes by. That is a key feature of waves that we will see in two types of waves. We're going to look today at two types of waves, and let me grab us a new piece of paper here. We're going to look today at two types of waves. The first type of wave that we'll be looking at is a transverse wave. Let's take a look at it. What I'm about to show you here is a nice PhET simulation. You can literally type into Google PhET simulation, transverse wave, and it'll come up with this little simulation here that you can look at and play with, and you can do all kinds of fun things with it. When you check out this PhET simulation, which I highly recommend that you do, you're going to see that there are lots of little toggles that you can play with. For right now, I have mine in the oscillate position, and I've changed the amplitude and the frequency to be things that I like, so you can make all those changes yourself. The reason why I highly recommend that you look up this PhET simulation is because when I make my videos using Google Screencast, my videos are a little bit laggy, so you can't always see exactly the kind of effects that I want you to be able to see for each of these waves. I will describe to you what you should be seeing, but you're definitely going to have to look for it. If you look up this simulation by yourself, then you can see it totally easily, and it's like brilliant and perfect. So there's my caveat for that. Okay, here I have a PhET simulation that's going to show you what a transverse wave looks like. A transverse wave is the type of wave that you are picturing in your brain when I say the word wave. When I say, hey, picture a wave, you're thinking a wave that probably goes like this. That's a transverse wave. I'll show you what it looks like, and we'll hit play on the simulation. There it is. This is a transverse wave. Here's what I want you to notice that is going to be very difficult to recognize on the on my video of the PhET simulation, but if you look up, like if you just Google PhET simulation transverse wave, you'll be able to see this really clearly, is that the little particles that are like each little bead on the string of this wave is not traveling with the wave. Instead, it's just moving up and down in its own position. This is made very clear on the PhET simulation by these little colored beads. You can take a look. The first one is the easiest to see. Can you see that that first colored bead, the green one, is just moving up and down? The wave is propagating this way, which means the wave is going this way, out the window. But each little bead is just oscillating up and down in its place. In other words, the matter does not travel. The wave travels, but the matter does not travel. You can notice, actually, wait, let me try it this way and see if you can see this a little bit better. See if you can see how when I send out just one wave pulse, it's not going to be it's not going to be that the beads are moving. The beads are going to stay right where they are. It's just going to be the wave that travels. Check it out. Watch. Do you see it? Check one more time. Notice how each bead stays right where it is. It just bounces up and then comes back down again to make the wave. This is a transverse wave here. What we're going to do first is we're going to label all the different parts of a transverse wave. There are lots of different parts of a transverse wave that we can talk about. I'm going to go back over here to my drawing, and I'm going to draw a picture of a transverse wave. You should do so too in your notes. But first, a definition of a transverse wave. A transverse wave is a wave in which the motion of the medium is perpendicular to the direction of propagation. I'll write that down, and then I'll say it one more time as I write it down. It's a wave in which the motion of the medium is perpendicular to the direction of the wave's propagation. Here's what that means. I'll draw you a little picture here. Perfect. This is a transverse wave. We say that if the wave is going this way, I'm going to say that this way is the direction of the wave propagation. Propagation just means which way is the wave actually going. If the wave is actually going this way, each little particle on this wave bounces up and down like this. Notice that each little particle moves perpendicular to the direction of the wave propagation. We can see this again if we look back at the PhET simulation. Do you see how the wave is moving this way? The wave is moving this way, but each little particle is moving up and down. That is characteristic of a transverse wave. That's what it means to be a transverse wave, is that even though the wave moves this way, the particles in the wave move up and down. So, if we take a look at this transverse wave, there are a lot of different attributes or a lot of different parts of this transverse wave that we can label. The first thing that I like to label is here, I like to label this center line right here that goes straight through the center of the wave. This center line is what we call the equilibrium position. It's where the medium would be if there was no wave happening in it. In this PhET simulation, it's right here, right along there. You can see that they've actually marked right here where that is with a nice dotted line. That's where the rope would be if there was no wave in it. It's the equilibrium position. The next thing that you need to know that I like to label here is all of the, wow, that is not what I wanted. Okay, is all of the little peaks of a transverse wave. We call these peaks the crests of the transverse wave. And all of the low points on the transverse wave, here and here and here, ooh, wait, let's change out our color really quick so we can distinguish. Let's make it red. All of the low points on the transverse wave here and here, we call these the troughs. The crests are the peaks and the troughs are the valleys. Now, there's another attribute, or there are two ways really to talk about how big a wave is. The first way to talk about how big a wave is to talk about how tall it is, and the second way to talk about how big a wave is to talk about how long a wave is. The way that we talk about how big a wave is we talk about the amplitude of a wave, which I'll show you here. The amplitude of a wave is the height of the wave, which we measure from the equilibrium position to the top of the crest, like this. Or alternatively, from the equilibrium position to the trough, like this. Both of these distances represent the amplitude or the height of the wave. We represent the amplitude with the capital letter A, and the units of amplitude are meters because it's a height. The next thing that we can measure is the length of a wave. The length of the wave is the distance between two successive identical parts of the wave, which is a bit of a mouthful, but what it means is it's the distance between two crests, or the distance between two troughs, or the distance between one little up point right here and another little up point right there. The distance between two successive identical parts of the wave is what we call the wavelength. It's the length of the wave. And when we had to choose a letter to represent wavelength, we ran out of letters in the English alphabet, and so we chose the Greek letter that looks the most like a wave, the Greek letter lambda. Now, when you're drawing a lambda for me, you start by drawing a little curvy kind of wave shape, and then you give it a nice little leg. But if you are not the type of person who likes drawing fancy swirly curves and you would like to just keep things nice and straightforward and simple, then you can draw it like this for me, and I'll know what you mean. That's wavelength. Wavelength, because it's a length, has units, you could probably guess, of meters. So there are two ways to talk about the size of a wave. You can talk about its amplitude, how tall it is, or you could talk about its length, how long it is. We often associate the amplitude of a wave with the energy of a wave. This is pretty intuitive. You could imagine that if I asked you to make some sort of low amplitude wave, you would say, okay, and you take a little rope with your hand and you'd go like this. Just like that. Not that big of a deal. Very low energy activity. But if I told you to make a wave with a very large amplitude, you would say, okay, and you'd wave your hand like this. Which one takes more energy? Pretty intuitive. The big amplitude wave takes way more energy to make than the small amplitude wave. And so big amplitude waves tend to have way more energy than small amplitude waves. One other thing that's true, just a quick little thing to notice here. Do you see how every wave is born from something going up and down and up and down and up and down and up and down? Like, for example, if I were to attach a little spring right here. Get out of the way. Oh, no, thank you. If I were to attach a little spring right here, and that little spring were to bounce up and down and up and down and up and down and up and down, do you see how that little spring, if it were tied onto a rope, could create a wave? All waves start from little particles or from bigger particles or from hands bouncing up and down holding onto a rope. They all start from something acting like a spring or acting like a pendulum, going up and down and up and down and up and down and up and down. That's a little bit on transverse waves. We're now going to look at transverse waves to show us 3 more properties of waves that all have to do with the motion of a wave. Hey, don't waves exhibit simple harmonic motion? Don't they do that up and down and up and down and up and down thing that's so characteristic of simple harmonic motion? That means that waves have a frequency and a period that we can measure. The frequency of a wave is the number of waves per time. The period of a wave is the time it takes between 2 waves. I like to imagine my childhood at Waterworld. Now, I don't know if you've ever been to Waterworld before, but if you have, then you know all about the wave pool at Waterworld. It is every child's greatest dream to get to go to Waterworld and to play in the wave pool. Now, I remember being but a wee child, and I went into the very big wave pool at Waterworld. They have a big wave pool and a small wave pool. And I went into the big wave pool at Waterworld, and you know the time when it happens, when the buzzer goes off, the waves start, and all the children scream for joy. Well, I was one of those children screaming for joy when the buzzer went off and the waves began. But then, as they got closer and closer and closer, fear and dread started to make their home inside of my heart as I watched the approaching waves. And sure enough, when the first wave hit me, I got completely pummeled under the water. I swam up to the surface, gasped for air, but right as I was getting a good breath, the next wave came down and pummeled on top of me. I gasped for air again and tried to reach the surface of the water and get some air, but then the next wave came. The frequency of the waves is how many waves are coming at me in a certain amount of time. The period of the waves is how much time I have between each wave before the next wave comes to pummel me. You could calculate both of these by counting the number of waves and dividing it by the number of time, or dividing it by the amount of time it took to observe that many waves. When you count waves, by the way, you should always count the same part of the wave. So you could count crests or you could count troughs. And then you can calculate the period by dividing the amount of time you see between two waves, like the amount of time between the first crest and the next crest. That's frequency and period. As you know from when we talked about springs and pendulums, because they're just flip-flop inside out of each other, the frequency is equal to 1 over the period, and the period is equal to 1 over the frequency. So those are some equations that you can keep in your back pocket. The last thing that we're going to talk about here, looking at transverse waves, is wave speed. Wave speed is how fast a wave is going. And wave speed depends on how, really, truly, what medium the wave is in. Some mediums allow waves to travel faster, other mediums allow waves to travel slower. We can take a look at this here in our simulation. If I change the tension in the string, which is effectively changing the medium, like to a very low tension, well, actually, let's start at a medium tension, and you can see what happens. If I change the tension in the string to a very low tension, do you see how the waves start to move differently versus if I put it at a very high tension? You can see that the waves, again, change their speed when I change the medium. So the medium determines how fast the waves move through the medium. If we go back over here, we can calculate the speed of a wave using this equation. We'll use this equation, but we'll use it over here, I guess. Okay. V equals delta x over delta t. Old news, yes? Well, in this case, a good length to measure for the distance that a wave travels is a wavelength. And the amount of time it takes for a wave to travel one wavelength is 1 period, because that's the amount of time between two waves. Then, I'm going to erase this stuff here. Sorry. Okay. This you could actually use as an official equation for wave speed. However, by convention, it's not the one that we officially use. What we officially use is we say, well, 1 over the period, isn't that just a frequency? And so we replace 1 over the period with the frequency, and we get V equals frequency times lambda, which is wavelength, or as I like to say, V equals flamda. And that is an equation that you can add to your bag of tricks. We'll talk way more about V equals flamda when we talk about waves transferring between different mediums. Okay, that was quite a bit on transverse waves and other general wave properties like frequency and the period and wave speed. Let's talk about longitudinal waves. A longitudinal wave is our second type of wave for today. Longitudinal. And we're going to take a look here at a simulation of a longitudinal wave. Once again, it's going to be way easier to see this simulation if you look it up. So literally, if you look up longitudinal wave simulation, you can find this one. It's a really beautiful one. Here's how a longitudinal wave works. You can see here I have matter, 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 all here stacked up like this. What's going to happen when I create a longitudinal wave, I'll hit play right here. What's going to happen, you can see that you have here some matter that is squishing and pulling back. It moves forward and then it moves back. When it moves forward, it squishes, it presses on the matter in front of it, and then that matter presses on the matter in front of it, which presses on the matter in front of it, which presses on the matter in front of it, which presses on the matter in front of it, and you get this little squish that travels all the way through. Notice, once again, that each little particle, each little line doesn't travel through with the wave. It actually stays exactly where it is. You can see this with the red line and with the green line here. Notice that the red line is just moving back and forth in place like this. It's not traveling to the other end. It's just going back and forth in one place. The wave direction, oh wow, that was terrible. Let's try that again. This goes back and forth in one place. The wave travels one way, this way. That's the direction of the wave's propagation. A longitudinal wave is a wave in which the matter moves parallel to the direction of the wave, but notice that the matter still is not traveling. It's just oscillating back and forth in its place. This is a longitudinal wave. Oh, well, let's clear this out. Here we go. A longitudinal wave is a wave in which the motion of the medium is parallel to the direction of the propagation of the wave. And it looks like this. You have some matter right here that's really compressed, then other matter that's spread out, then other matter right here that's compressed, then some more matter that's spread out, then other matter right here that's compressed. There are really two parts to a longitudinal wave. There's the squished up parts here, and we call the squished up parts compressions. These are compressions. We call the stretched out parts of a longitudinal wave here and here, we call them rarefactions. Rarefactions. A lot of students want to call these rarefractions, which is totally fair because it totally sounds like a word, but it's not a word. The correct word is rarefactions. Rarefactions. And that's a longitudinal wave. Notice once again, like we said while looking at the simulation, you have, I'll do this in black, you have the direction of the wave propagation going this way. Here's the direction of the wave propagation. But each little piece of matter in the wave is oscillating back and forth. Kind of like you could imagine if I attached a little pendulum here onto the end of this piece of matter here. And every time the pendulum swung back this way, it pulled it back, and every time the pendulum swung this way, it pushed it forward. All waves are just a result of little particles, either acting like pendulums and going back and forth, or acting like springs and going back and forth. That's what all waves come from. Now, a few examples of longitudinal waves. Longitudinal waves feel a little more abstract to us, but some examples. I actually like to use a giant slinky in class, and I take a giant slinky and I just push on one end of the slinky. Hey, could you see how if you looked at this thing, this could be the side view of a slinky, where this would be coils that are tight together and this would be coils that are spread out? Another example, and the prime example that we'll be talking about the rest of this unit, is sound waves. Sound waves come when a little bit of air gets squished by a vibration, and then that air squishes the next little bit of air because the air molecules run into the air molecules in front of them, and those run into the air molecules in front of them, and those run into the air molecules in front of them, and the little squish travels all the way across the room, and that's how sound waves move. And that, ladies and gentlemen, is everything that you need to know about waves for today. Your homework is a quiz that is located on Google Classroom. So you can find and access that quiz and answer those questions to the best of your ability. Well, I hope you have a wonderful rest of your day. Thanks for joining us on Waves. Bye, guys.